In this video, we're going to look at the reverse process of differentiating. So this is determining an antiderivative. Okay, so far in this course we've been looking for derivatives. Now we're going to look for functions that have specified derivatives. So we're looking for what function gave this derivative. Okay, this can be useful because in previous videos, our functions provided the total amount of some quantity, okay, cost, revenue, temperature, distance, etc., etc. But derivatives give their rates of change. Sometimes when you're trying to model a given scenario, it's hard to find the total amount of the quantity, but it might be easier to determine their rates of change or to predict the rate of change or how the rate of change is affected by certain things. So because of this, sometimes the antiderivative is actually a more useful tool for us. So that's why we're going to study it here. So the reverse of finding a derivative is known as anti-differentiation. So instead of differentiation for derivatives, we have anti-differentiations. So we want to determine the function from its derivative. Okay, so this is the idea of an antiderivative. So if you have capital F prime of x is equal to little f of x, okay, so when I take the derivative of capital F, I get little f. That means that capital F is actually the antiderivative of little f. Okay, so let's just do some basic examples. So for each of these, we want to find the capital F of x that has these derivatives. Okay, so for the first one, I want capital F of x so that f prime of x is equal to 2. Okay, so I want a function that has derivative of 2. Okay, so we want to come up with one, so maybe we could use f of x is equal to 2x. Okay, that would be a function that has derivative equal to 2. Okay, let's try a slightly harder one. What if I want the derivative 3x squared? So this one looks familiar. You might remember that the function x cubed has derivative 3x squared. So we could use capital F of x to be the function x cubed. Okay, so that would be one for that one. What about cosine of x? So do we remember a function that has derivative cosine of x? Okay, so I want the derivative with respect to x of something to equal cos of x. Okay, now what is that something? Well, if you remember, sine of x has derivative cos of x. So if I use capital F of x to be sine of x, then I have derivative cosine of x. Now, are these the only antiderivatives that will give these derivatives? So we want to think, could we have another function, let's say f1 of x? Could we think of something else that has derivative of 2? Well, what if I add a number? What if I take the f of x to be 2x plus 7? Okay, then the derivative of this is 2 plus 0, right? The derivative of 7 is 0, so it's just 2. So we also have derivative of 2. So this would be another example of a function that has that derivative. So it's possible. So when we take a derivative, each function has exactly one derivative. But when we're doing the antiderivative, there's many functions that have the same derivative. So there's many different antiderivatives. Okay, so the answer here is no. And it turns out that we could add a constant is the only thing you can do. Okay, so that's what this theorem says. So if capital F of x and capital G of x are both antiderivatives of a function little f of x, then there is a constant c so that if you subtract them, doesn't matter what order, you just get this constant. Or another way to say it is that one of them is the other one plus some constant. Okay, so in other words, they differ by only a constant. Okay, so the only way you can change them is by adding a constant to it. What that tells us, because we could add any constant, there's infinitely many things that we could add on here, we get infinitely many different antiderivatives for each derivative. Okay, so we're going to have some notation so that we can talk about all the antiderivatives at the same time. Okay, because they all sort of look the same. So, if I have a function little f of x, the family of all of its antiderivatives can be described using what we call the indefinite integral. Okay, and this is what the notation looks like. So I'm going to write the notation first. So I have this weird symbol, and then I have f of x dx, which I'm going to talk about, and then we would write that this equals capital F of x plus c. Okay, so this is the notation. Now I'm just going to talk about each of these things. Okay, so this weird symbol, this is called the integration symbol. Okay, now it looks like a stretched out S, and it's supposed to. Okay, that actually comes from something which we're going to talk about later in a different video, but it makes sense to use that shape. Okay, now the f of x, okay, this thing we call the integrand. You don't really need to remember this word, okay, but that's what it's called. This is the function you want the antiderivative of. Okay, so that's the thing that we want to find the antiderivative of. Okay, the dx here, this is telling you your variable of integration. Okay, integration is kind of another way to say antidifferentiation. They're related to each other. So it's your variable of integration. So like when we were doing the derivative, remember that we did I'll write it up here. So d over dx of some function. Okay, and the dx here was telling us that x was our variable. Okay, that's the same thing that this is doing here. Okay, so it's saying that x is the variable that we're trying to find the antiderivative with respect to. Okay, so this is when we take the derivative. Similarly, when we do the antiderivative. Okay, now the capital F of x, this is any antiderivative. Okay, so you can find your favorite one of little f of x and put it here. Normally we take one that doesn't have a constant added to it, but if you want to have an extra constant, that's fine. Okay, so you're allowed to take any antiderivative, and then because we want an infinite family of them and they all differ by a constant, this c is a constant, and it's called the constant of integration. Okay, so because c can be any number, okay, we get an infinite family of answers here, or antiderivatives. Okay, so c is just some constant. Okay, so that's what we do to say that we want to find all the antiderivatives of a given derivative of a given function. Okay, so that's the idea. Let's just do a few examples here. So in this first one, we want to find the indefinite integral. So we want to evaluate this. So x is our variable, and our function, okay, is this little f of x is 5x to the 4. So that means that we want a function that has derivative 5x to the 4. Okay, now this looks like the result of a power rule. So I think I'm going to pick x to the 5 to be my capital F of x. Okay, because then I know capital F prime of x is 5x to the 4, which is equal to that. Little f of x, okay? But then I have to add my constant of integration. Okay, so this answer here is going to be x to the 5 plus c. Now, if we wanted to check that this is true, you can always check your answers here by taking the derivative. So if I take the derivative of x to the 5 plus c, well, the derivative says I can do this separately. So I take the derivative of x to the 5 and I add the derivative of c. The derivative of x to the 5 is 5x to the 4. And the derivative of c, because c is a constant, is 0. So I just get 5x to the 4, which was my f of x, the integrand, which is what I wanted. So I know that I found an antiderivative. In fact, because of this plus c, I found all possible antiderivatives. Okay, slightly harder one. So my f of x, little f of x, is 2e to the 2x. So I want to know a function that has derivative 2e to the 2x. Now, if we remember our derivatives of our exponential functions, we know that if I have the derivative of e to the x, I get e to the x. So because I have here my derivative e to the 2x, it's likely that I'm going to have e to the 2x in my antiderivative. Because in order to get e to the 2x in my derivative, I need to have an e to the 2x to start with. So if I just try, so maybe I'll do this down here. So let's just try f of x is e to the 2x. What would that mean that my derivative is? Because I want to find an antiderivative. So I need something that has derivative 2e to the 2x. So I'd have to use the chain rule here. So e to the 2x has derivative e to the 2x times the derivative of the exponent, which is 2. Okay, now notice that this is little f of x. So e to the 2x is an antiderivative. So that means this I could write as e to the 2x plus c. Okay, and that's going to be an antiderivative. Or that's going to be all the antiderivatives, actually. So that's what my indefinite integral should look like. So as I mentioned, I left it in here actually. I thought I took it out. The notation for the indefinite integral, this is a Leibniz notation. It's an elongated s, okay, and it's related to a sum, okay, and that's why the s, okay, but we're going to see that later. So we want to do we want to find some more antiderivatives or evaluate some more indefinite integrals. I want to do a few that have the power rule. So let's just remember what the power rule looks like. So if I wanted to take the derivative with respect to x of some power of x, remember we bring the power down and then it's x to the n minus 1. Okay, so notice that our exponent decreases by 1 when we take the derivative. So what that means is that when we want to take the antiderivative, we want to do the opposite. So it means that probably our function has to come from a power that's 1 bigger. So if it's a power of x, as it is in example 4 here, okay, so my f of x, my little f of x, is x to the power 4, it probably had to come from an x to the 5. Okay, because when I differentiate, the power goes down by 1. Okay, so I probably want to be 1 power bigger. Now, what happens if I take the derivative here? Well, we already took this one, I think. So this is 5x to the 4. So I got a 5 that we don't want. So we want a way to get rid of that. So if we think about the constant multiple rule, so when we take the derivative, if there's a constant, we just pull it out. So what if I had the constant 1/5 here? Oops. So if I had this whole thing to times by 1/5, then I would get f prime of x is x to the 4, which is what I want. So that means that this whole thing had to have a 1/5 as well. So what we end up getting for one antiderivative, we could use 1/5 x to the power 5. And then I want to add my constant. Okay, so this is giving all the antiderivatives. Now let's just check that that works by taking the derivative. So if I take the derivative of this, okay, I'm going to have 1/5 times 5x to the 4 plus 0, because the constant is derivative 0. And then we can see that the 5 here and the 5 here are going to cancel out. And I'm just going to get x to the 4, which is my little f of x, which is what I wanted. So using this idea, we have this idea of an analogous version for antiderivatives of the power rule. Okay, I call it the reverse power rule. So if you want to integrate or find the indefinite integral and your function is a power of x, okay, so x to some n, what you can do is you take x to the power 1 higher. Okay, so it was n, so it's going to be n plus 1. But because when I take the derivative, this n plus 1 is going to drop down, I want to get rid of it. So what I'm going to do is multiply this by 1 over n plus 1. Okay, and that's going to give me an antiderivative. So here is what we call the reverse power rule. Okay, now one comment I have here, does this work for all n? Okay, is there an n value that you might think is a problem? Because the power rule works for all n's. Okay, but the reverse power rule does have an issue. So I'm dividing at some point by n plus 1, which means I don't want to divide by 0. So we want to make sure, we need to be careful because this does not hold for when n plus 1 is equal to 0, which is when n equals -1. Okay, this is a bad n value. Okay, so when n is -1, you can't use this rule. Okay, but for all other n's, it works. Okay, so we're going to try and figure out how to handle this n equals -1 case later on. But let's just do a couple of examples using this rule. So for the first one, I just have the function x. Okay, so this is my little f of x is x to the power 1. Okay, so that little x there is my integrand. So it looks like it satisfies the conditions for our reverse power rule. So it means that this should have come from an x squared. Okay. Well, in fact, let's use the rules exactly. So let me just erase that square here. So if I use the rule, it should be x to the 1 plus 1 times 1 over 1 plus 1, okay, plus c. So that's 1 over 2 x squared plus c. Okay, so that is this gives me all my antiderivatives. Let's just check by taking the derivative. I'm not going to put the c in because we know that that goes to 0 anyway. So if I take the derivative of 1/2 x squared, I'm going to get 1/2 times 2x, which is just x. So that's my integrand. I'm happy. Okay, so maybe I'll just highlight. So this thing here matches what's in my integral, or my indefinite integral. Okay, let's try another one. Now this one doesn't look like it matches, right? It's not x to some power. But remember that we could rewrite it. Okay, so 1 over x squared is actually x to the -2. Okay, so now it does match, and the exponent -2, okay, that's not -1, so the theorem should work. So if we use this theorem, it should be 1 over -2 plus 1 times x to the -2 plus 1 plus c. Negative 2 plus 1 is negative 1. So it's 1 over negative 1, x to the negative 1 plus c. So we just get negative, x to the negative 1 is 1 over x. So we get negative 1 over x plus c. Okay, so that's my family of antiderivatives. And again, we could check by taking the derivative. So 1 over x, I'm just going to write that as x to the minus 1. Again, I'm not going to include the plus c because we know that that goes to 0. So this is going to be negative, and then negative 1 x to the 1 less is negative 2. The two negatives cancel out, and I just get 1 over x squared, which is my f of x. Okay, so this thing here matches that thing there. So that means that we found an antiderivative. So we have all of them. So notice here that we rewrote our integrand. Okay, if you're able, you're encouraged to do so. So you're allowed to manipulate the integrand if you need to simplify it. You're allowed to do that. So sometimes it helps to simplify first, just like it does with derivatives. But what you want to remember is you have to keep the integral symbol and the dx, okay, or whatever it is, until you actually determine the antiderivative. Okay, so you have to keep it, just like when we're doing the limits, you have to keep your limit as x goes to 0, or limit or whatever. You have to keep that notation all the way until you actually evaluate the limit. Same idea here, or when you're simplifying, if you use the d by dx notation, you have to keep that until you actually take the derivative. Okay, same idea here. So you want to be careful about your notation. So what about when n is negative 1? So there's this weird case that we ignored for a minute. So what does that look like? It means that we want the antiderivative of x to the minus 1 dx. X to the minus 1 is actually 1 over x dx. So what that means is we want capital F of x so that capital F of x, or capital F prime of x, is equal to 1 over x. So can we think of a function that has derivative 1 over x? Okay, now hopefully we have this in our mind. This is one that we've seen before. So we know the derivative of ln of x is 1 over x. Okay, or we can actually say, remember, I mentioned it at the time when we talked about the derivatives for the logs. We also know more generally that the derivative of ln of absolute value x is actually 1 over x. Okay, so this one has a larger domain. So it's slightly more general. So that's the one we use for this special case. Okay, so this is actually ln absolute value x plus c. Okay, so I'm just going to write that rule down here. So if you have x equals negative 1 case, you want the indefinite integral of x to the minus 1 dx, or 1 over x dx. What you're going to do is write ln absolute value x and then add your constant, because ln of absolute value x has derivative 1 over x. Okay, so that's the special case. That's when, maybe I'll just write here. So this is the n equals negative 1 case in our reverse power rule. There's some other derivative rules that have analogs, okay, for the antiderivative. So the constant multiple rule. So if you want the indefinite integral of a constant times some function of x, just like you can with the derivative, you can pull the constant outside. So this is k times the indefinite integral of f of x dx. Okay, so you're allowed to bring the constant out. So then if, maybe I'll just write, well, okay, so if capital F of x is an antiderivative, then we could write this as k times capital F of x plus c. So this is if capital F prime of x is equal to little f. So that says that capital F of x is an antiderivative. Now, one thing that I should point out here is that I don't actually need brackets like this. So I don't have to multiply the k with the c, just because, so this c is some constant. So k times c is just another constant. So it doesn't actually change anything. You're still adding a constant. Okay, so k times c is just some other c. So you don't have to worry about that. So let's just put this in a box here. Okay, so another one is the sum or difference rule. So if you want an indefinite integral of some little f of x plus or minus some little g of x, okay, you can actually do these separately. So you could say it's the indefinite integral of f of x dx plus or minus the indefinite integral of g of x dx. Okay, so it doesn't, you can do the parts separately when they're added or subtracted, just like you could with derivatives. So let's do an example that uses this. So let's say we want we want to find the indefinite integral 6u squared minus 8u plus 1 du. Okay, so here u is our variable, okay, just to be a bit different. So let me just write this down. Minus 8u plus 1 du. So the sum or difference rule says that I can do this, each one of these separately. So 6u squared du, the indefinite integral, minus the indefinite integral of 8u du, plus the indefinite integral of 1 du. Okay, now the constant multiple rule says I can pull out all the constants, so the 6 can come out. And then I have the indefinite integral of u squared du minus the 8 times the integral of u du. And then the 1, that doesn't matter. Okay, this is just du, you might see it. So now I can use the reverse power rule. So I know that u squared had to come from u cubed. Oops. Should be a 3, u cubed, but then I need to divide by 3, and I actually only need to add the plus c at the end. Okay, so because I don't need c1, c2, and c3. That's, if I add those up, I just get some other c. Okay, so I'm just going to put a plus c at the very end here. So u du, this is like u to the power 1, so that means it had to come from u squared, which means I need a 1 over 2 out front. And then what has derivative 1? Okay, well that's just u, right? So u to the power 1. You could think about this as u to the power 0, okay, because then the reverse power rule says it should be 1 over 0 plus 1, u to the 0 plus 1, which is just u. Okay, so if you want, you can think of it like that. And then I have my plus c. Okay, so simplifying, I'm going to get 2u cubed minus 4u squared plus u plus c. Okay, so this would be my family of antiderivatives that have derivative 6u squared minus 8u plus 1. Okay, and again, you could check by taking the derivative. Oops, sorry. Check. So if we take the derivative with respect to u, I'm just going to not write it again. So 2u cubed, this is going to be 2 times 3u squared minus 4 times 2u plus 1 plus the 0 for the c. So that's 6u squared minus 8u plus 1. that was our integrand, f of u. Okay, so we know that we got the right answer here. Now, we've seen quite a few examples where we get an infinite family of functions with the given derivative. But we often want the exact function that has a certain derivative. So in order to do that, we need an extra piece of information. Okay, this piece is known as an initial condition. Okay, so it's some extra data, some extra value that enables us to know which function, which value of c we actually need. So the idea, let me just draw you a little picture here. The idea here is when you get your antiderivatives, so here's my function. Okay, I'm just going to do a really basic antiderivative. So let's say it's like the parabola. Okay, so if your antiderivative, or one antiderivative, is say x squared, then your family of antiderivatives are just moving this graph, shifting it up and down, so that your derivatives, the slopes are the same no matter what. Okay, so it just shifts it up and down. So if you have some extra condition, so for instance, you say you know that this point is on your graph, then you know that you need this particular c value. You want to be on that specific graph. Okay, so that's the idea. So here, if we know the slope of the tangent line of a function is given by this equation here, so that's for any point x, and we know the function passes through this point, we can find the equation for the function. So we're not going to get an infinite family. Okay, so the m, the slope, being 3 root x plus 2, that means that this is actually the derivative of a function, right? So the slope of the tangent equals the derivative. Okay, we should probably have that ingrained in our minds right now. So what we can do first is take the antiderivative of this. So our function, I'm going to call it little f of x because I used f prime there. Our function is going to be the antiderivative of this slope, okay, where x is our variable. Okay, now the sum rule and the constant multiple rule says that I could rewrite this as 3 root x dx plus 2 dx, the integral. Okay, now I might want to rewrite root x as x to the 1/2, so it looks like a power of x. Oh, and I could pull out the 2 here if I want. So now the antiderivative of x to the 1/2, this is going to be 1 over 1/2 plus 1, x to the 1/2 plus 1. Okay, and then something that has derivative 2 is just 2x, and then I get my plus c. Okay, so if I simplify this, this is 1 over 3 over 2, x to the 3 over 2, plus 2x, 2x plus c. So 1 over 3 over 2 is the same as 2/3. Okay, and then the 3's can cancel, so I end up with 2x to the 3/2 plus 2x plus c. So this is what my function looks like. Now I do want to point something out before I move on here. So when you have a fraction for your exponent, if you add 1 to it on the exponent, okay, you always do that, and then you divide by the same thing. Okay, this bottom here, when you have a fraction, this is often going to be a fraction as well. And when you do 1 over a fraction, it's actually just the flip of the fraction. Okay, so notice here I have 3 over 2, whereas I end up with 2/3. So that's when you bring this down, you're going to get 6 over 6, or the 3's cancel and the 2's cancel. So you can, instead of doing 1 over the thing, you can just flip it if you want, once you get comfortable. Okay, so that's our function. Okay, but we also know that I'm going to rewrite this. So we also know that f of 4 is equal to 10. Okay, so this part is from this point being on the curve. Okay, so what that means is if I plug in 4, I should get 10. So 2 times 4 to the 3 over 2 plus 2 times 4 plus c. And I can use this to figure out what my c value is. Okay, so 2, so I'm going to take the square root of 4 is 2, and then cube that. This is going to be 8. So I get 10. This is 16 plus 8. That's 24 plus c. So that means that c has to be minus 14. Okay, so that tells me that the f of x that I actually want, that has both the right slope and the right point, is actually 2x to the 3 over 2 plus 2x minus 14. Okay, so this is actually the function that I have that satisfies both conditions. Okay, so this is actually sometimes known as an initial value problem because you have this extra condition that you know. Okay, we're going to see more of those later, but here we can use that extra condition to figure out exactly what the c value is.